Welcome to this next segment on fuel and energy source characteristics within the generation dispatch module. The objectives of this segment are to cover how energy is measured, then describe the different energy characteristics of oil, gas, coal, uranium, and renewables, and then show you how to calculate the average energy content from quantities of different energy sources. And then from that, calculate the BTU, British Thermal Unit requirement, for various megawatt hour requirements of electrical output. And then finally, calculate the price per British Thermal Unit of fuels based upon the energy content and the current market price. So this is really laying the foundation of understanding how much energy is stored in different fuels, what is the price of that fuel, and then how that converts to electricity. And based upon this input, of course, everything you learn here is a necessary foundation to come up with the right dispatch of the overall generators throughout the system. In the North America, we still use the British units of measure. So the British Thermal Unit is the amount of energy to raise 1 pound of water by 1 degree Fahrenheit. We scale that to millions of BTUs. So each M is for 1,000. So 1,000 times 1,000 BTUs is 1 million. And 1 kilowatt hour of electricity is equivalent, if we have 100% efficiency, to 3.413 million BTUs. Right now, if we look at the sources of generation for producing kilowatt hours in 2011, this is a pie chart showing that we are heavily dominated by coal at 42%, and then natural gas is the next largest at 25%, nuclear at 19%, hydro at 8%, wind growing quickly is now at 3%, other renewables at 2%, and petroleum has been becoming less and less, down to 1% for the total of 100. What we'll expect to see is natural gas grow really strongly as a result of our reduced price for natural gas, and a large amount of growth in the wind, with coal tending to shrink. There is a lot of interest right now with renewable portfolio mandates for renewable sources, and this typically includes reserves that are not limited by any finite form, such as hydro, solar, wind, and geothermal. Now, it's really important to have an understanding of the energy content of different fuels, and so here we have a wide variety of different types of energy. 1 cubic foot of natural gas is 1.03 million BTUs. 1 hour of sunlight on a 1 square meter solar panel is 3.4. A gallon of fuel oil, 5.8. 1 ton of bituminous coal is 22. And surprisingly, 1 hour of 10 meter per second wind on the largest 44 meter blades is 406 million BTUs. And of course, at the very high end, we have refined uranium at 3,587. So those as the inherent amount of energy, both in fuels as well as the renewable sources. Let's take each one of the different fuel types in turn and learn a little more about the varieties and their sources. So coal is basically a mix of hydrocarbons, water, sulfur, and nitrogen. And it can be categorized into different amounts of coal depending upon the age, the pressure, and the heat content. So clearly, the denser coals have been in the ground under higher pressure for longer periods of time. And as we go through these different types, we get increased heat content, increased pressure, and age. And I like to use the memory aid of Lisbon: lignite, subbituminous, bituminous, and anthracite. So if you think Lisbon and you're getting increasing age and pressure and heat content as you go through the L through to the N. Two of the very popular types for generating electricity are subbituminous, which has high water and a lower heating, and bituminous, which has high sulfur, and that's very common in the Midwest and eastern U.S. We'll see that the anthracite is the purest, but it tends to be available, well, the highest heat content, but it's available in the Pennsylvania region, and it tends to be used for very specialized applications. As far as applications for generating electricity, the most popular are the lignites, which we find throughout the North and South Dakotas, and the subbituminous, which we find throughout the Montana and the Wyoming. And what we tend to have is large thermal units, coal units in North, South Dakota, and their power tends to be shipped towards the east on both high voltage AC and DC lines. And then in Montana, we have large coal-fired plants which tend to tie into the western United States and ship their power into the Oregon and Washington areas. For those areas that have a high amount of sulfur, we often see liquefied bed systems, which are especially good at heating the coal to such a level that they're able to extract the sulfur. Now, what we're seeing in the current environment is through a combination of EPA restrictions on a very tight time frame to meet the mercury air toxic standards, as well as a pressure to help the environment by making sure that the water that is put out into the oceans and rivers does not have a temperature rise to it. We're seeing a lot of money even having to be allocated to retrofit existing coal plants, or the option that, of course, is to not go through that retrofit and retire them. So the American Coalition for Clean Coal Electricity is projecting a very significant retirement rate of coal generation. They're projecting that 241 coal generators producing 36,000 megawatts will be decommissioned in the next 3 to 5 years, 11% of our current energy production, and that will mostly affect the states of Ohio, Pennsylvania, West Virginia, and North Carolina. Those states themselves will lose 18,000 megawatts. There is a very strong lobby from a combination of the Edison Electric Institute, the International Brotherhood of Electrical Workers, to say, please, we need more time to actually allow those retrofits to take place and give the owners of those units a chance to and an option to keep them online and running. The other thing that is a pushback on coal is the relatively high amount of CO2 that is generated, and with the prospect of carbon fuel credits and a tax on actual carbon dioxide emitted into the atmosphere, it's having a chilling effect on utilities. Even though there's a tremendous amount of coal in the ground, these restrictions are having a dampening effect on utilities investing in new coal plants. One exception to that is the AEP Mountaineer coal plant in New Haven, West Virginia. It is the world's first with carbon capture and sequestration, CCS, and they are storing 100,000 metric tons of CO2 a year in an underground cavern at 7,200 feet. There's obviously a lot of additional costs associated with that, but the fact is that there is so much coal available, it's economically priced. There are organizations pioneering a way to keep clean coal on the market by using innovative technology. Another approach is to have integrated coal gasification conversions, where you take the coal, you convert it to a gas, and then you burn the gas in gas turbines. But that is a relatively new technology which hasn't been scaled up to massive production at this point. All right, moving on to the next major fuel is natural gas. Basically a mix of light hydrocarbons, mainly methane, CH4, and there are tremendous gas reservoirs that stand alone or may be part of an oil reserve. There is no sulfur dioxide, and it has 1/3 the CO2 of coal. So we're seeing a tremendous advantage in terms of greenhouse gas emissions. Most of the natural gas comes from Texas, Louisiana, Oklahoma, New Mexico, Wyoming. But there is a major game changer with the natural gas situation. Just has an incredible effect. We see this on the cover of Time magazine. This rock could power the world. Shale gas is trapped in shale rock formations under the earth, and we can release that by drilling down to around 10,000 feet and then doing a horizontal drill and injecting a fluid into that rock, and the pressure of that fluid causes the rock to separate apart. So that's called the fracturing. And as that rock separates apart, it releases the gas that's been trapped inside of it. So we have seen some amazing combinations of DOE-funded research, high technology, entrepreneurial oil drilling technology, all brought together to make this a very major, serious contender to solving our energy problems. They have microseismic imaging. When that rock fractures, there's a popping sound. And so what they do is they have listening devices, a whole bunch of arrays that send out a sound signal, and then that signal bounces back, and they're able to determine where that actual fracturing happened. So they're able to very precisely determine through a technique called tomography where the fracturing is occurring, map that out, and make very good decisions about should they put in another drilling hole here and go in this direction, and obviously keep track of the sources of where the gas is coming from. So all that is coming together to have a huge impact. This map shows what the United States gas shale plays and the ones that are actually in service today. And look at this one. Here we have major amounts of natural gas right next to a lot of the load in the eastern United States. This has driven down the cost of natural gas just to an amazingly low levels, and we'll see the trend that's happened over the last 10 years. And it's happened to the point now, some of the major concerns, like in ISO New England, is gas is so competitive, they're going to gas to such a strong amount, the major contingencies now are losing the actual gas pipelines into a region because there's only so many of those pipelines. And when you have all of your eggs in one basket, and that basket fed by a pipeline, you have to be really concerned about the likelihood of losing that key source. There are natural gas in shale formations all over the world, and so basically the projections are that shale will add another 40% to the entire worldwide reserves of natural gas. So this shows you basically the dramatic impact we're seeing on the marketplace. We take $13 per million BTU at the Henry Hub in July of 2008, all the way down to less than $3 per million BTUs in May of 2012. Tremendous impact on the market. It is making natural gas clearly very competitive with coal, and there are a lot of other reasons why it is taking off in the marketplace. Clearly, we're building on a existing pipeline infrastructure, 160 pipeline companies, 285,000 miles of pipe, transporting close to 120 billion cubic feet per year. This industry has been, like we said, was deregulated prior to the electric industry, but there's still some natures about the way that industry is handled, which gives us challenges from an electrical point of view, and we'll cover those. Hurricanes can affect offshore production clearly. They have to also serve gas pumping stations. And when we have a low pressure situation, because there may be some pumping station, maybe the emergency has caused some pumping stations to be out of service, or maybe the source is not keeping up with the demand, what happens is the low pressure happens throughout a whole region, and so multiple generators all have to be derated or taken offline. So more and more we have to think about the combined effect during emergencies of the gas dependencies and the electrical dependencies together. As we're putting our restoration plans together, we saw in Hurricane Katrina, the utility there, Entergy, had to totally reorient their restoration plan because they realized that there were some gasoline pipelines where the pumps were without electricity, and there are major parts of the U.S. that weren't able to get gasoline. So all of a sudden there was a major reorientation that has to happen. So I encourage everyone in the utility business to take a real close look at all the pumping stations in their service territory and think through the possible consequences of a total system-wide blackout. One of the things that affects the scheduling of natural gas powered devices is what's called a take or pay contract. Basically, the buyer pays the same amount even if the product is not used. And this means that you've got to look at the amount of energy that you've committed to over a certain period of time. You just can't look at your decision right now and make a decision to say, based upon all my resources, this is the right decision. You have to say, well, if I make this decision to use this amount of gas now, and I have this policy based upon my load and my expected demand, how much am I going to use over the next month to make sure that I do either use all the energy that's available or not make an assumption of using too much. And so there are some similar constraints there to hydro units. With hydro, you have a fixed amount of energy constraint as well as the actual constraint of your capacity. We have programs called like unit commitment programs, the programs that determine when the unit should start up, how long they should stay up for, and when they should shut down, have to take care of those types of take or pay contracts. And then what also, as I mentioned, we're seeing the loss of one or two pipelines can be a major contingency for an entire region of the country. This is the first time I've mentioned the unit commitment and the economic dispatch. So the economic dispatch makes the decision at one point in time, assuming what units are online and available and running. The unit commitment determines when the unit should be started up and shut down, and what order does that take place. So there's a constant balancing between, do I leave a large coal-fired unit running through the weekend, or do I shut it down? I have significant shutdown and startup costs. It takes people and fuel to heat all the machinery and the boilers and all the equipment and the metal up to a certain temperature. So I'm constantly making that trade-off that, well, I might even leave it running during the weekend and pay someone to take my power rather than go through the startup and shutdown cost. I'll just spend a little bit of time on oil because it is currently used for just less than 1% of U.S. power generation. U.S. consumption of over 20 million barrels a day, and almost half of that is in automobiles. And as engineers that work in the power industry, I believe we should be doing everything we can to reduce our dependence on oil totally, and that means converting to electric vehicles and becoming free from the hold of oil-producing countries. All right, let's spend a little bit of time on nuclear. Just reviewing some of the basics. It's derived from nuclear fission. Atoms contain protons and neutrons. Under the nuclear fission, the neutron strikes the nucleus of uranium and it is absorbed. And then that atom splits into two other atoms, and in that process it releases a lot of heat and 2 or 3 more neutrons. And those neutrons go off at high speed and collide into other uranium atoms, and that creates the chain reaction. So 1 kilogram of enriched U-235 uranium has 3,600 million BTUs. That 1 kilogram is equivalent to 150 tons of coal. That uranium is loaded as little pellets into tubes, and there are control rods that go down into the reactor to absorb those neutrons to control the level of reactivity. So in the U.S., we've had approximately there's 104 nuclear power plants in operation today. That's been pretty steady since the 1990s. We've seen a few retirements, and through here it's been basically flat with no new plants built. But as a result of major advancements in the reactor designs and safety and standardized configurations which have been licensed from the NRC, we are seeing a resurgence in new nuclear reactors, primarily in the southeast. So what we see is in the southeast we have very little wind. And then throughout this area there's a tremendous amount of wind. So in the west we have a very attractive way of getting new capacity. But in the southeast they've had a long tradition of reliably running nuclear reactors, and in many cases those companies are going back and adding new units to the existing ground of the facilities that they have. So as one example, we have within Southern Company and Georgia Power, we have the Hatch 1 and 2 existing units, and then there is the Vogtle 1 and 2 units, and they'll be adding the Vogtle 3 and 4 units to complement that power plant. So there are many jobs available in all aspects of design, maintenance, construction for those plants. So summarizing, there's about 1 cubic meter of waste per year generated by a plant. New reactors have inbuilt safety features where the actual control rods will come on down without any electric supply, and that the water will keep circulating through the inertia of large flywheels driving that through the shutdown process. And a key is that the NRC is standardizing on the designs, and people are repeating those versus building customized designs for different plants. Currently, nuclear supplies about 20% of U.S. electricity, and we need about 1 unit per year to be built, and we'll maintain that percentage. So as we can see, in the southeast, there definitely is a strong push for nuclear, and we'll get into the details later about how do we actually manage those types of units during the dispatch. Let's now look at hydro generation. As an example, in the Northwest, we've been extremely blessed with a very comprehensive hydro system, total of 24,000 megawatts coming off the Columbia River, coming down from Canada, and the Snake River coming in from the Rocky Mountains, with a very large amount of that coming from the Grand Coulee Dam. So the benefits are it's low cost, no air pollution, no thermal pollution, no carbon dioxide, about 100 gigawatts total US, 6.5% installed capacity. Characteristics are the output increases with the head, the rate of flow, the efficiency of the turbines. They can start up very quickly and ramp quickly. These are the favorite power plants to be used for black start because you can bring them up with very little additional electricity required. In some cases, they're great for pump storage. You take an area where you pump the water up during the nighttime when electricity is low in price, and you generate it back in the daytime. And they can be used for peak shaving. We'll show why there's a natural fit to use hydro to run it at the time of the day. All right, moving on to the next type of fuel, wind. We're seeing a very aggressive development for wind. As we see from this map, this is meters per second, but if we convert it through here with the magenta is 19 miles per hour, and with the at the 6.5 level meters per second, we're at 14 miles an hour. So clearly there's tremendous wind resources throughout the center of the U.S. and through and of course in Washington State we have a tremendous amount of wind, with it peaking in certain valley areas like on the Columbia Gorge and out in the southeastern part. And it's just a matter of how to take that wind, put it up onto the high voltage transmission lines and move it to the loads. So the wind is encouraging a lot of investment. We have what's called competitive renewable energy zones in Texas. Independent investors are building transmission lines to take the wind from the northwest part of the state and move that to the major population centers. There are many new jobs opening up in some of these control centers because they are having to take on, put new control centers in place to move that power to the loads. This shows a summary of the various costs of fuels. So if we take the actual cost to buy a barrel or 1,000 cubic feet or a ton, and then we take the amount of energy that is inherent in that amount of fuel, we get the dollars per million BTUs. So this is the common denominator. Even though we have lots of ways in which this fuel comes at us, whether it's oil or gas or coal, we convert it to a single basis of dollars for the million BTUs. And that clearly shows the difference and how natural gas, with it dropping in price, is really right down there with coal. And so because natural gas has 1/3 the carbon dioxide content, and we can build those units very quickly, that's where all the investment is happening right now as far as building new thermal plants. I won't go through all the detail in the math except to say that if we have a 100% efficient plant, then that is 3.41 MBTUs per kilowatt hour. If we assume a 30% efficient plant, then we need to divide that number there by 0.3. And so this is the amount of heat going into the plant for the kilowatt hours out. So the idea is to do production costing, we have to look at the total amount of BTUs to generate a certain amount of kilowatt hours over a period of time. And as an example, we put a spreadsheet together to say if we had 1,200 megawatts of generation and it's an 80% capacity factor. In other words, a capacity factor is that that unit is not running at full output the whole time. That its energy, if we took the maximum potential energy it could generate at full output and then took the actual amount of energy it generates because it goes up and down a little bit, that's called capacity factor. And then we take the efficiency. Well, we can take each type of these fuels and say, how much would we spend during a month to run that unit under these conditions for 31 days? And we see the amount of cost to run a generator is pretty significant. Natural gas, $28 million for a month. Uranium, $4 million. Lignite coal is $6.5 million. When I looked up the price for lignite coal, it was only $8 per ton. I'm wondering if there's something funny about that number, okay? But that's for your homework to find out. But the point is, you can go on the web, you can look up the prices of these different types of fuels today. The rest of it is just mathematics to do the conversion. But the point I'm making here is the decisions that utilities make in the balancing area, and as you, whether you're a balancing authority operator or you're someone in the marketing department and you're running production cost programs to decide which units you should start up, shut down, what sources should you use to buy power, it has to be driven by an understanding of the economics of what your different options are. And I think that's the thing that we want to do through this class, is to give you an insight into what is driving the different types of fuels, how they are used, how they're transported, how they convert to electricity, so that you're not just rotely following rules in a marketing situation. In any marketing situation, there are always day-by-day patterns that you can follow, but when things change, that's when you have to adapt. And I think if you have the insight of how everything is working together, and you can kind of have an idea behind the numbers in the spreadsheet, you may be able to come up with some improved approaches as things change. So, in conclusion, in this module, our objectives have been to show you how fuel is gathered and used, the characteristics, the general market conditions, how to calculate BTUs for megawatts, give you an idea of the average content for different types of fuels, and then figure out, based upon a certain energy profile and price, how many dollars are required to serve that need. Thank you.